Good afternoon. My talk is about analysis of the physical mechanisms limiting reliability and performance of GaN-based hands. This is the outline of my presentation. I will first talk about the high electric field degradations in GaN hands. So this work is aimed at investigating the location of trap generation in GaN hands with the ultimate goal of providing insight about the physical mechanism triggering this trap generation. Samples are unpassivated GaN hands. In spite of the absence of passivation, these devices show a negligible gate lag, and this can be seen from this figure, in which we see that there are no differences between pulse measurements and DC measurements. A first reliability test was performed on these devices by keeping these devices at a VDS of 10 volts, a VDS of 16 volts, and a VGS of 0 volts up to 150 hours. As can be seen, the important results are summarized in this slide. So there is a drop in the DC current and an amplification of the gate lag, and a decrease in the gate current. In our simulations, we considered different scenarios, but the most important ones were by considering trap generation at the surface and in the buffer, or in all the three layers, so namely the surface, in the barrier, and in the buffer. In this way, we could reproduce the amplification of gate lag and the decrease in the gate current, as well as the drop in the DC current, as can be seen from this figure. In a second reliability test, devices were kept in off-state conditions by biasing devices at a VDS of 32 volts and a VGS of minus 6 volts. As in the case of power state stress, we can see a drop of the DC ID current and an amplification of gate lag, as well as a drop in the gate current. However, from the GM characteristics, we can see that there is a different behavior. After power stress, GM drops only at high VGS, while after off-state stress, GM drops uniformly at all VGS. This can be correlated with a different localization of the generated traps. So we considered different lengths of the damaged region from 1/16 up to 1/2 of the gate drain spacing. What we have found is that increasing the length of the damaged region amplifies the drop of the GM at high VGS. So we can conclude that power state stress is consistent with a damaged region which tend to extend toward the drain. As a matter of fact, if we see the longitudinal electrical field at the early stage of the stress, we can see that it peaks at the drain end of the channel. After that, in this way, hot electrons can generate traps only within a narrow region close to the gate edge. After that, the electric field peak will move to higher lengths, and consequently, the generated, the damaged region will tend to extend toward the drains, as the electrical field will move to higher lengths. The only way we could reproduce the degradation modes in the case of state stress is that of considering a small region close to the gate with a significant degradation of parameter transport of the channel. In this figure, we can see that the GM is dropping rigidly at all VGSs by increasing the degradation in the mobility and the saturation velocity. This is similar to what we have obtained for GM after off-state stress. So we can conclude that in the case of off-state stress, strain enhancement by vertical electrical field is likely to play a major role. Now let's move to the characterization and the analysis of trap-related effects in GaN hems. Devices, the samples are short gate hems, FET hems, and Schottky diodes, all having the same epitaxial structure, with the exception of Schottky diodes, which do not have the cap layer. This is an Arrhenius plot from DLTS measurements on FET hems. As we can see, the three traps are detected, which I will call trap A, B, and C. This table summarizes the outcomes from the other characterization techniques. So when DLTS is applied on diodes, only trap B and C are detected, while trap A is not detected. This suggests that traps B and C are located in the bulk, while trap A is located at the surface. On the other hand, the other techniques such as GM dispersion and current mode IDLTS and gate lag provide the same indication of the for the three traps. So the problem is now from these measurements we are sure that trap A is at the surface, while traps B and C we have inconsistent indications. So to try to explain this result, we have performed a measurement, a gate lag in the same conditions as for the IDLTS mode, and we obtained this ID transient at a temperature of 300 Kelvin. So this suggests that the trap responsible for this transient is trap B. But this kind of transient is consistent with a hole-like trap, so which is generally generally consistent with a surface trap signature. But the most interesting thing is that if VGS is switched to a value close to the pinch-off, the behavior changes and become that of a buffer trap signature. So to try to understand this kind of contrasting behavior, we use this simulations, and we obtain the same behavior. We can obtain the same behavior provided that traps B or C are placed in the buffer. So what's the reason for that? We have obtained two contrasting behavior for the same trap. Now let's start with the case in which VGS is stepped to a value which is sufficiently higher than the pinch-off. We can see that in this case the channel is not completely depleted, while electrons are injected deep into buffer and are trapped in the buffer. The trapping of electrons in the buffer, we can see from here that the ionized density, trap density of traps in the buffer are increasing. This tells us that they are capturing electrons, and this explains the decrease in transient in the ID transient shown in the previous slide. Now, in the case of when the step of VGS is to a value which is close to the pinch-off, we have that the density of electrons in the channel is much smaller in this case, and we can see from the density of ionized buffer traps that this density is decreasing with increasing time, indicating that the effect in this case is the emission of electrons from traps. So this explains the behavior of in the transient. This explains the increasing transient which we have seen in the previous slide. Now I will talk about the mechanisms of RF current collapse in HAMS. In this work, the devices used are passivated GAN-ALGAN HAMS. This is a gate lag measurement in which VGS is switched from totally off conditions to totally on conditions. As we can see here, the gate lag is negligible at these voltages, indicating that passivation is effective. To try to understand the impact of passivations in these devices, two-dimensional simulations were carried out, and this table summarizes the parameters of traps adopted in the simulations and extracted previously. So trap A is a donor-like trap, while traps B and C are acceptor-like traps. As we can see here, the simulated gate lag with and without passivation. So in the case of passivated devices, we can see in agreement with the experimental result that the gate lag is negligible in the case of passivated devices, while in the case of unpassivated devices a significant gate lag emerges. This is the variation of ionized donor density. As we can see here, the density of ionized donor is increasing with increasing density, with the increasing time. So this suggests that the donor-like traps are emitting electrons, and this explains the shown behavior of unpassivated devices. In the case of passivated devices, the change in the ionized donor density in order to recover the steady state conditions after the application of the turn-on step is much smaller in this case, and this is why the transient is negligible in the case of passivated device. This can be explained by this figure by showing the electrical field at the surface, and as we can see, the electrical field in passivated device is reduced. The reduced electrical field in passivated device makes the electron injection from the gate much smaller than in the unpassivated device, so inhibiting the electron capture from surface trap. Now, if the VGS is stepped to a much more negative value, current collapse emerges, and we can see here that there are three slow transients with different time constants. So one question arises: so if we have two kinds of traps and we have three transients, so we can ask ourselves if buffer traps can contribute to a pure gate lag measurement. So to answer to this question, two-dimensional measurements, two-dimensional simulations were adopted, and we can see from this. So we have reproduced the same condition of current collapses with three slow transients, and we can see that the first transient is originated from electron trapping to traps, to buffer traps which are located under the gate. As we can see from this figure, the density of ionized buffer traps located in this region is decreasing with increasing time. Now, concerning as far as the second transient is concerned, we can see that in the corresponding interval, we can see that surface traps are emitting electrons in this time interval. So we can conclude that the second transient is due to electron emission from surface traps. And finally, for the third transient, we can see here that the ionized density of buffer traps located this time in the drain axis region, they are decreasing with increasing time. So this proves that they are emitting electrons. This is a band diagram of the device at equilibrium conditions. As we can see that the Fermi lever is not pinned at the trap, at the surface trap, unless a certain value of the NA is reached. So this suggests us that we can obtain that large surface potential can coexist with the shallow traps, inducing current collapse effects characterized by a short time constant. Now I will say something about the kink effect in Grahams. In these characteristics, we can see a sort of kink effect when increasing VDS from 0 to 20, while this effect disappears when the measurements, if the measurements is performed from 20 to 0 volts. This is a simulated ID waveform in response to a VDS step from 3 to 6 volts. We can obtain an increase in transient if we include donor-like traps in the barrier. Only in this case we can obtain an increase in transients, which suggests that kink effect can be explained by the electron trapping into barrier traps and a subsequent emission after a certain level of electrical field is reached. The first decrease in transient is the commonly obtained transient after drain lag measurement. As a matter of fact, the density of ionized buffer traps are decreasing with the increasing time. So this proves that the buffer traps are capturing electrons, and in the corresponding time interval of transient A. While in the correspondent time interval of transient B, we can see that the ionized trap density of the barrier in the barrier are increasing with increasing time. So this demonstrates that the increase in transient is due to barrier traps. So in summary, we found that only the simultaneous generation of surface of traps at the surface and in the buffer can account for all the degradation modes observed experimentally. Moreover, from the GM curves, we can say that power stress is consistent with a damaged region, which tend to expand to the drain, while off-state stress is consistent with the generation of a small region close to the gate, plus degradation of transport parameters in the channel. Moreover, we have seen that both surface and the buffer traps can contribute to the gate lag, and we found also that passivation could be simply explained by the reduction of surface electrical field, which reduces the gate injection of electrons from gate to surface traps. Moreover, we have found that surface potentials, large surface potentials, can coexist with shallow traps, surface traps, which can induce current collapse effects characterized by a short time constant. Finally, kink effect can be explained by electron trapping to barrier traps and a subsequent emission of electrons after a critical, once a critical electrical field is reached. Thank you for your attention, and this is a list of my publications.
Thank you, Mustafa. Questions? Please.
Yes, it's always in the field of reliability, but it's another from another point of view. So I will be concerned about the packaging, about thermal effects, about the stress in the, so it's always about reliability of GaN but from another point of view.
So thank you. This was the last presentation, and that's the end of this afternoon session. We will see, thank you to all the speakers, obviously, and thanks also to the audience. And we will see tomorrow morning for the presentation of the students of the second and first years. And thank you. Good evening.